Today we're going to be graphing linear inequalities. The solution to a linear inequality statement is really, if there is a solution, there is an infinite number of ordered pairs that will satisfy. And so in order to show all of them, instead of trying to provide a list of all of the ordered pairs that will make a particular inequality true, we show the solution by graphing and shading the proper side of what we call a boundary line. And so that's going to be involved. I'm going to show you how to do that, how to graph these linear inequalities to show the solution. And then we're going to be looking at application, and that typically means some sort of real-life context problem, also known as a word problem for those of you who just do not like word problems. And I'm going to cover that part of this objective as part of a homework help video. So I'm actually going to do one of your homework problems, which happens to be a word problem. So this lesson will deal with just graphing linear inequalities. So let's take a look at some examples. Here is my inequality statement, and before I do anything else with these inequalities, I should verify that the inequality represented is in slope-intercept form. And this one is, so there's no additional work to be done, but if it were not, I would need to change it into slope-intercept form first, because what I'm actually going to be doing is graphing what is known as the boundary line, which would be the line represented by this equation. Okay, so the equation, we need to go back and review how do we graph a line that's in slope-intercept form like this. Well, this 1 represents the y-intercept, and the 3/2 that's in front of the x represents the slope. And remember, we can think of slope as rise over run. The change in y, that's up 3, and over the change in x. So I did two positive directions, a positive 3 and a positive 2. And I could also do two negatives, because negative 3 divided by negative 2 is still positive 3/2. And so now with those three dots, and I typically, when we're graphing lines, I'm going to ask you to provide 3 points. I'm just setting up my line draw tool here. And I notice I'm ready to draw this boundary line, but I notice that this reads greater than, not greater than or equal to. So for that reason, I am going to do a dotted line for this boundary line. Okay, let me get a running start here. So I'm drawing through these 3 points. This is called my boundary line. And then I'm going to shade the appropriate side, because remember, the solution to this would be an infinite number of ordered pairs. First of all, what we've shown is ordered pairs that will not make this true. This dotted line means that the ordered pairs that fall on this particular line don't make this work. But the greater than side of this line shows all of the ordered pairs that will make this true. And so I usually make the statement greater than means above the line for lines like this that have a particular slope. Less than means below the line. And if you don't trust yourself that you shaded correctly, you can always do a point. For example, if possible, use the origin, plugging in for x and y and into the inequality, and see what the result is. So let's just do that little test up here. Remember, x and y are both 0 at the origin. So if I replaced x and y with the origin points, I would have 0 is greater than 3/2 times 0 plus 1. 0 is greater than 0 plus 1. And finally I get to 0 is greater than 1. Well, that's not true. So what I've just proven is that on the side of this boundary line that contains the point 0, 0, none of these points on this side will make this true. So I've done the right thing. I've shaded the other side because these ordered pairs, any of them that I wanted to pick, anything on this side of the boundary line will make this true. So let's just do an example of that. Let's just take any point we want that's on the upper side or the shaded side of this boundary line. So here is the point -2, -4. Okay. So if I want some, I'm sorry, +4. -2, +4. If I want some assurance that I have done the right thing, I can just do this little test. 4 for y is greater than 3/2 times -2 plus 1. Okay, 3/2 times -2, that's -6/2, which is -3 plus 1. 4 is greater than -2. Well, that is certainly true. So now I proved it the negative way. I proved that none of these points can work because 0, 0 didn't work. And then I proved it another way. Since -2, 4 worked, all of these have to work. All right, so I just want you to get an idea, what does it mean to have a solution to a linear inequality? Okay, so for this one, we are looking at what we call standard form. If this were an equation, it would be the standard form of a linear equation. X followed by y equals a constant. And before I start graphing, this is important, we need to change this into slope-intercept form, which means I need to first subtract the x term from both sides. Then I need to divide by 2 on both sides. And now I'm ready to draw the graph of the boundary line. The line itself would be graphing this. The inequality is what tells us how to shade. Okay, so first let's think about this boundary line. And it has a y-intercept of +2. It has a slope of -2. So from this red dot, I'm going to go down 2. Which means since that's a negative move, I need to combine that with a positive move. And I'll do the same thing going the other way. I could do a +2 combined with a -1. Now this time when I draw the boundary line, since it says or equal to, this is going to be a solid, which basically says that any point that falls on the line itself is part of our solution set. Okay, so there's the boundary line, and I'm going to do the shading based on the inequality. It says less than, and less than for these lines like this that have slope are below the line. Less than is always below the line. And then once again, if you wanted some assurance, just do the origin. It's easy math. You could probably do it mentally. The 0, 0, if x is 0 and y is 0, then obviously 0 plus 0 is 0. And you can verify pretty quickly that 0 is less than or equal to 4. I get some people that get a little confused there, and they say, well, it's not equal to, but remember, it's not less than and equal to, it's less than or. It doesn't have to be both, it just has to be one of these. And so it does satisfy, it does fall on the side that we've shaded green, and so I just have a check, I have some assurance that I did the right thing. Okay, some of your problems will involve this. They will give you a graph, and it's going to be your job to come up with the equation represented. So it's really the reverse of what we just did. So it's not too bad. I would first of all locate the y-intercept. That's 1 in this case, +1. Then see if you can figure out the slope. Find a couple of points that are easy to determine. And you can do rise over run, or you could do the slope formula if you wanted, y2 minus y1 using those 2 points. But I think it's easy enough just to do rise over run. So it looks like the slope in this case is going to be positive 2. So we just put that together. Remember, we're writing slope-intercept form. And I noticed that as far as the shading is concerned, it's shading above the line. And I just said earlier that above the line means greater than. So I'm going to show greater than. I'm not going to do or equal to because it's not a solid line. So I'm going to put my slope together with my y-intercept, and I get my answer to this particular problem. This inequality matches this graph. Okay, let's try this one. The lines that are just vertical like this or just horizontal tend to give people trouble. So for that reason, I'm going to dwell on this for just a minute. These lines that are vertical, here I have a vertical line that really is just drawn on top of the y-axis, and I shaded the left side of it. Well, lines like that, let me just do a few more just so you can get the idea. This particular line right here, for example, in blue, if I ask you for the equation for that line, well, it crosses 2, 4, 6, 8, 9. It crosses the x-axis only at 9. Okay, in other words, there's an x-intercept. There is no y-intercept ever. Only going to be crossing the x-axis at one point. And so therefore, if we were writing the equation for this blue line, we would say the equation would be x equals 9. Okay, vertical lines like this, when you're writing the equation form, you will say x equals just x, because we're never going to touch the y-axis. It'll be x equals a particular number. Where do we cross the x-axis? And now if I wanted to do the inequality, okay, now we got to do some shading, and the greater than side for this line would be the right side. Okay, just think of how the number line works. Numbers are getting bigger going to the right, smaller going to the left. Okay, so that's one example. Let's just take a look at another one just to make sure. If I drew a vertical line here, I'll just erase this one so you won't have a lot of lines to look at here. And I'm going to come back eventually to our actual homework example, which is the red line. But I just want to make sure everybody understands this. I get a little confusion about these vertical lines and the horizontal lines. So here my blue vertical line is crossing only the x-axis at one particular number, never going to cross the y-axis. So I'm going to write this equation in equation form. This would be x equals 5. Negative 5. I'm crossing the negative axis at negative 5. Okay. So when I do the shading, that's when what makes it an inequality. If I were to shade this side of the blue line, then I would be showing less than or equal to. The less than side for this vertical line is the left side. Okay, hopefully that makes sense. Let me see if I can undo all this, and then we'll get back to our example. Okay, let's just delete this one. So hopefully now you see how to do the correct answer for my red vertical line, which crosses the x-axis at 0. Okay, vertical lines always have to, if they're in equation form, they have to say x equals some number. Well, the vertical boundary line, if it were just the equation, would be x equals 0. Including the shading changes it to an inequality, in this case less than or equal to 0, since this is a solid line. Okay, so that would be the answer for my example number 4. Example number 5, well, this time, if you notice, I have a completely horizontal line that's never going to cross the x-axis. It only has a y-intercept, and it's going to cross the y-axis at negative 5. So the equation for that red line, if I just wanted the equation for it, I would say y equals -5. But when you include shading indicating one side or the other, indicating the solution set, that's what changes this equation into an inequality. And shading the underneath side of this, just think about how the numbers on the y-axis are getting smaller and smaller. They're getting less and less. So in this particular case, when I indicate shading, I'm going to use the inequality less than. I'm not going to do less than or equal to because that's not a solid line. The points on the line itself do not make this true. But the yellow region indicating the smaller, the less than, -5 will make this true. Okay, so hopefully you understand that the equations for vertical and horizontal lines. Okay, got one more of these. So I would pay attention first of all to the y-intercept. That's b is -3. The slope again is up 2, right 1, up 2, right 1. Slope is +2. And I've got a solid line and I'm shading above the line, so that's greater than equal to. And now I just use my number for slope as the coefficient of x, and then plus or minus the y-intercept. So those should be pretty easy for you. And that's all of the graphing part, and you've got a couple other word problems, and as I said earlier, I will provide some help on at least one of those and maybe give you some guidance on a couple others on my separate homework help video. So hopefully this will help you, and if you have any questions, let me know.